etc., and so on. So the project was basically proposed early this year. Then our little pandemic hit, so we had to basically put it a little bit on the back burner. But I'm very happy that especially Paul and Robin have been pushing to get this back on the agenda. And the IDC Executive Committee approved it earlier last year, and here we are. So I think this is a project that will be just as the other ones of great significance for the industry. It will be a collaborative effort. That's why we're sitting down with IADD for an IADC project, and listening also to our clients and a lot of different folks. So I think this is an excellent project to work together to keep our industry relevant for the years to come. And with that, I will give the word back to Robin, because I think there's a lot of other stuff that is very interesting to be discussed.
There is, thank you. Yeah, we have a packed agenda. Just to let everybody know, there will be a Q&A session. We've got some technical presentations coming up later. So we won't be having Q&A at the end of each speaker or at the end of each presentation. We will have a dedicated Q&A session after the end of the technical sessions. So feel free to put your questions in the Q&A box, and we'll be keeping an eye on that. So next, let's talk to someone that we see as the main beneficiary of all this technology and us improving the systems, the senior operator. So let's hand it over to Dustin Shell. Over to you, Dustin. Thanks. I think you're on mute, Dustin.
Yeah, technical difficulties. I mean, if anyone's done the Menti quiz this morning, I put that together. It's probably relatively obvious, for those of you who've done it, where I see the gaps are in the current grading system. And there's a wide variety of people on the call. Paul's going to go a bit more into what we're actually proposing, but the main idea going forward is that we'll actually have a set of codes that will more accurately describe the damage that's taken place, so that not only can we benchmark the runs, but we can further product development from a queryable type database. And really that along with helping bring up the knowledge level at the field base for why that damage may have occurred, we'll have a full system in the back end so that we can qualify and quantify the damages, and then further product development along. The old system, it is unlimited in the manner in which it can describe the damage and where on the drill bit. And we're planning to to build on that. I hope at the end of the day, it's not just a benefit for operators, but for the drill bit companies as well, and the associated vendors that that work in the drilling industry. It's not just about like I said, it's not just about the operators being able to have a database on their end. We're hoping that on the vendor side, they will as well be able to improve their product development by having a database that more clearly identifies where the areas of concern are and how and what the performance of those runs are. Maybe I'll turn it over to Paul.
Great, thank you. Thanks, Dustin. And thank you, by the way, thank you for putting that survey together. That was great. And that will help feed some of the projects that we know are going to be coming up as a result of what we're proposing. So yeah, over to you, Paul.
You bet. Thanks, guys. I teach within, Paul Pastusic, Drilling Mechanics Advisor, ExxonMobil. 42 years in the industry. One of the tasks that I do is to teach forensics within ExxonMobil and without ExxonMobil. I do teach a lot to other people, including our vendors, just to keep us all on the same page. And for a number of years now, we've known that you look at IEDC DOL codes, and one, because of subjectivity or interpretation, they don't really capture, let me say, the essence of what we really want in a forensics code. The other is, what are we trying to do with forensics? Is trying to get to a root cause, to some kind of corrective action. So, you know, we even if it, by the way, it's not all. I used to always say failure analysis. It doesn't have to be a failure. It could be a record run. It could be an outstanding run. Okay, now what are we going to do better, right? So we need to think about, you know, this in terms of our continuous improvement. So my short summary is the code's not sufficient to give us all of that level of detail we want. It's not clear, and I use an example of on one blade, it has 3 cutters that are brand new and absolutely pristine, and then 1 cutter is broken in half. So that would be graded in the current system of 4. So you average those together, divide by 4, and you get, it's 0, 0, 0, and 4, and you get a 1. Unfortunately, a broken cutter and broken in half is probably not a bit you put back in the ground, and somebody grades that a 1, and you'd go, sure, we'll rerun that bit or whatever. So, you know, it's the way we described it back in the day. I think we've learned a lot more about the level of detail and this cutter by cutter kind of analysis. The other thing is we're missing codes, the types of failure, the types of breakage on cutters, and it primarily, when we're talking about continuous improvement, mostly it's around the cutters themselves and the continuous improvement of them. And they have, good gracious, they have improved dramatically even in the last 5 years. And they made progress for the 20 years before that. The other thing that's missing, besides missing codes of certain types of fracture that's showing up today, the other thing is we don't really spend much time on the BHA. Just like when we look at the drill bit and we say, oh, that's telling me I was whirling down hole. Well, look at stabilizers, and they're wearing, you know, they may be wearing on one side, that's forward whirl, or they're rounded and they're, you know, it's reverse whirl, or it's tapered on the bottom end because of borehole spiraling. All of those are indications for me to do something different. And we barely talk about those things. So there's room for including other elements in the VHA. Sometimes we call it a motor failure. Sometimes we call it a back off. Sometimes we say it's a VHA failure. You can imagine trying to do a sort and study of that kind of thing. It's a little bit tough. So we just need to clarify it and get it right. I know there are many people working on this. We invited a few into this meeting, and, you know, just to kind of get a taste of what the current state of the art is and what people are working on. There were a lot of people that wanted to be here that asked, and we just said, okay, we'll have more meetings. We'll discuss this as we go forward. But the guys that are here today have some kind of product or something that is really close to commercial or is commercial and is being used. And so we said, okay, this is a good place to just talk about the state of the art. Like Robert said and Robin said, we proposed this. Actually, I originally was talking to Robin back in 2019 and said, oh, I don't have time in 2019, but 2020, my schedule is wide open. Well, that's my prediction for the future, right? I learned not to predict anymore. Anyway, we're finally getting there. I think we've got a lot of people lined up. I've got a lot of volunteers that have already expressed interest in doing this kind of work. And this meeting today for me is, one, it's a public announcement to get everybody out and interested, and people that maybe we didn't reach out to. And then, like I said, a quick state of the art. So, if I think about what we're trying to do at the rig site, we need to pick what's the next bit going in the ground and what's the next set of parameters we're going to run. It's like, I pulled out of the ground. I need that. I need the quick analysis, and I need to do it on the rig floor, because calling somebody in Houston, if I'm in Indonesia, is probably not going to get me the answer I want. So I need to be able to do something quickly. And then just as Dustin had said as well, if you want continuous improvement, you really need to look in the details. And if you look at 10 bits that are run side by side, the same part number, different serial number, you get to see details in terms of common modes of failure or slight weaknesses that just don't show up on a one run thing. And the best people to do that are the vendors of those products, whether that be motors or bits or whatever. So anyway, that's my goal today is to kind of announce that we're working on this. Number two, get volunteers for several kind of subcommittees and start moving forward. That's it. So anyway.
That's great. Thank you, Paul. And we'll be hearing from you later when we start to look at that requirement for volunteers. So now into our technical presentations. So we've got 6 presenters, each will have 10 minutes each. As I said before, put your questions in the Q&A box. And so what we'll see is, I mean, one reason this is timely now is you'll see that there are a lot of methods now, as you can imagine with facial recognition and LiDAR and laser, etc., of looking at bits and describing what we're seeing. But and everybody will have their own proprietary methods of describing that, and that's fair enough. But we decided we also need a universal method that these systems can feed into. So there may be proprietary systems, but we also need something that's universal where we can all agree and where we can compare one system with another. So our first technical presentation.
Robin, if I can interrupt just for a second, there
Yep.
is a question from Chaitanya of Empati to the panelists. Says, Dustin, Paul, shouldn't we be extending the queryable database conversation to all bit records and DDRs? It seems like the entire industry can collaborate much better if these were digitally available and standardized.
Yes.
Thanks, Jim. Good answer.
Typing a response to him right now, and yes, short answer is yes. How's that? I'll type in the answer so that people that are not online will get my the rest of my text. But yes, so Tanya, you're right on 100%.
Yeah, from the DDR standpoint, there is an XML schema, to be able to transfer information back and forth in a standardized way as well. So, but here also, yes, the more we can combine and correlate, the better it is.
That's great. Thanks, guys. Thank you, Jim. So back to our technical presentation. The first one is from William Moss of Hughes Christensen. So clearly the drill manufacturers have been working hard on this particular challenge. So we're going to hand over to you, William.
Hey, Robin, can you hear me?
Yeah, sure.
Okay, I'm going to go ahead and share my screen.
Okay.
Okay, can you guys see that?
Yep, we got that.
Yes, we
Okay.
can. Hey, by the way, Jim, did you announce that you are recording this for future reference for people?
I did not, but we are recording this, and it will be available as long as the presenters give permission to do so.
Thank you.
Great. Thanks.
Okay. Thank you. So to get started, I'm going to talk about an application that we've been developing at Baker Hughes called Instagrade. Just an overview, what it is it's a computer vision PDC bit dole grading application. So it's based on the IADC dole grading requirements with the addition of individual cutter wear state and dole characteristics. The reason why we developed this was because dole grading is subjective, right? Everyone has their opinion of what the dole grade is going to be. And a lot of times it's either incomplete or inaccurate. And the current IADC system doesn't support per cutter resolution. So that was one of the things that we wanted to add. It was developed in partnership with one of the Baker Hughes enterprise research teams. They kind of led the computer vision model development, and we led the integration and the SME side of it. So, the contributors here, application owner, Sheldon, Curtis, Chaitanya, and myself. And really the value added from the application is to minimize the subjectivity in dole grading and improve efficiencies in operations and promote correctness and completeness of the bit data. How it works, we've got one object detection model. We feed in a blade image and it detects the cutters. It determines a bounding box coordinates for each one of the cutters so that we can take a portion of that original image and feed that into 2 additional models. That object detection model currently only supports primary PDC cutters. It doesn't support backup cutters or shaped elements, inserts, carbide inserts. There's 2 classification models. The first model is a wear state. This predicts the wear state of the cutter. So, that integer scale 0 through 8, we're looking at improving that either to a half resolution or even maybe to a quarter resolution. That's really going to depend on how well we can get the users to mark the cutters during the training. The second model is a dole characteristic. So this determines whether the cutter is, broken tooth, chipped tooth, lost cutter, etc. And really, these are cutter level classifications. It doesn't include classifications that would be given at the global level, like at the entire bit, if it was a ring out or if it was a core out. When we train the data, the cutter detection, this is relatively easy. We start with an image of the blade, and a user goes in and draws bounding boxes around each one of the cutters, and we label the cutters, and we do that for many images, and then we train that model to detect what a cutter is. The 2 classification models are a little bit more complex. What we did is we had our drill bits application engineers run through 6,000 single cutter images, and they specified what the wear state was and what the dole classification was. So we built an application that pulled down these images from the cloud. They could set the wear state, set the classification, and then hit next. It pulled the next image. So we used our SMEs here within Baker Hughes to build that training data set. We did provide some guidelines, the basic 0 through 8 wear state, and also the dole characteristics that were really specific to an individual cutter. The way the application is used is as the application produces results, the user needs to confirm whether the model predicted the right state and characteristic. And if it doesn't, they're expected to make that change. And then all of the data that's generated from the application can be reused into training the model in the future. So just getting started, user takes dole photos either with a camera phone or a digital camera. The required image is a picture of the bit box, and really we want to use that for OCR in the future so that we can do optical character recognition, so we can get metadata about the bit, the serial number, the part number, etc. We want a picture of the bit record, and that's for the same. In the future, we want to be able to do OCR on the bit record and produce, pull out all of the operator specifics, the rig, and the performance metrics. And then we need top views and isometric views, and those are used just in preparing the customer presentation. And then we get kind of in the meat of it, which is the individual blades. And I took this 5-bladed bit here and showed the images that I used to feed into the model. And essentially, it's a single image of the blade that captures all of the cutters. So then access to the application, it resides on a platform called Drilling Insights, it's web-based and it's accessible from a PC or mobile device. And the Instagrade application was written for a mobile device. The idea is, the user is in the field. They want to get on the internet on their phone, take some pictures, upload it, and get a dole grade created immediately. So there is some data entry that's required, the bit serial number. And we use the serial number to access, design type information like the bit size, the type, the blade count, cutter counts, cutter metadata, and that's used for either pre-populating some of the data in the report, or it's used in confirming some of the model results. There's additional metadata like the customer, the rig, bit performance that's used in generating the report as well. And then the user starts the upload process. So I want to show you guys the results. And so once all the blades are processed, and this happens relatively quickly, within 30 seconds, we start getting results back. So here we've got blade 1, and we can see bounding boxes around each one of the cutters. So it's correctly identified all of the cutters. And then there's a tag that has the wear state and the dole characteristic for each one of the cutters. Like I said, the application is mobile. We do have this, scroll bar at the bottom of it, and hopefully I've got a few minutes here I can show the application. So we've got a scroll bar here at the bottom of it where you can go through the individual blades and do some confirmation of, making sure that what the model predicted was correct, or you can make changes. So here's the rest of those 5 blades, the remaining 4 blades. And it correctly identifies all of the cutters and all of these blades, and it makes its predictions. So I'm going to go ahead and show you guys the application. Okay. So can you guys see the Chrome window?
Yeah, looks like it's loading. There we go.
Okay.
Yep.
Yep.
Okay, so like I said, it was developed for mobile. So I've got my Chrome here displaying as an iPhone 6, 7, or 8 Plus. And it is accessible, from a phone directly over the internet. It doesn't require a VPN. And I've already uploaded the images. That takes a few minutes to go through uploading all the images. So I've uploaded the images and I've let it process. And I just want to show you guys, kind of the interactivity here within the application. This is a different bit than what I was showing in the presentation. This was, I think, a 6-blade run with a customer out in West Texas. So each one of the cutters, we can click on the wear state and dole characteristic. And if I didn't agree with what the model predicts, I can select what the wear state is going to be, and I can also select the characteristic, and then I can save that data. And like I said, all the data that's generated here from the model and the users making that confirmation is going to be fed back into the training of it to improve those models. So pretty easily, we can go through, kind of scroll and look at all of the different blades here. And in this case, I think the model struggled a little bit with the shockwave cutters. So I've gone through and made some adjustments. The models were all trained based on a planar face PDC cutter. So this would be, the more data that we can produce here with the shockwave cutters, the better it's going to be at predicting these dole states as well. The way that we've got the application set up right now is, it does require a Baker Hughes drill bit serial number so that we can get that metadata, so that it is specific to our designs at this point. But I think there is room to expand the application so that it doesn't have to be bit specific. We could take out some of the kind of checks in there based on cutter count and the number of cutters per blade, et cetera. That's all I've got, Rob.
That's great. Thank you. And I'm sure that'll be generating a lot of questions. So feel free, everyone, to stick your questions there in the Q&A box. Thanks, Will. Next speaker is Chris Probst, who's with Halliburton. So straight over to you, Chris.
And hey, Roman, just to remind everybody, we'll hold questions at the end of all of these presentations. So just write your question down or put it in the Q&A, and we'll answer them all at once.
That's right. Thanks, Paul.
Thanks, Robin. Can everyone see my screen okay?
Yep. It looks though it's not yet in presentation mode, Chris. We're seeing
Is it? Okay.
the next slide coming up as well.
Just a second. Okay, is that better?
Yep, that's it. Thanks.
Okay. All right, thanks, Robin. So my name is Chris Probst, and I am the Director of Technology for Halliburton Drill Bits and Services. So before I get started, I'd just like to say thanks to Robin, Paul, Dustin, and IADD for letting us participate in this conversation. I think this is a really important topic and one that has a lot of potential to really change how we drive performance with drill bits and cutters. So with that, I'll kind of just get into it. You know, this slide is meant to just kind of set the stage for what the historical dull grading process is. I think pretty much everyone on the call is probably pretty familiar with this. And Paul, you and Dustin talked quite a bit on it already, so I'm not going to go too far into it. But essentially, as we all know, from a historical perspective, the current dull grading process is you average the severity of damage for your inner cutting structure and give it a number. You average the severity of your outer cutting structure and assign a number. And then you essentially identify primary wear or failure characteristic. So as has been mentioned already, there's some kind of obvious limitations to this system. One, there's a lot of inherent subjectivity based on who is evaluating and doing the dull grading. But two, there's a lot of information lost in this system. As Paul was mentioning, you know, this is a kind of a good visual representation of what Paul was describing, where if you look at the inner cutting structure on this particular bit, yeah, we've got two broken cutters and say 6 or 7 green cutters. And so maybe that averages out to a 2, but in reality, it's important to know the details that those, you know, cutters 3 and 4 on blade 5 were broken and the others were green. So that's a lot of kind of fidelity of data that's lost when we just capture the normal IADC code. And similar with the dull characteristic information. You know, this is classified as a chipped tooth dull. But if you look at kind of the detailed picture on the right of that individual blade, you can see, yeah, we have some chipping, but we also have some D-lands and some spalls, and we have, you know, a cutter right there in the middle that looks a little bit more like abrasive wear. And so all of that information will be lost if we just only capture the IADC dull grade. So that really just kind of sets the stage for this whole conversation today. And what do we do about it? What are the next steps? How do we resolve that problem? And so this slide is kind of an overview of the system that we've developed. You know, when we talk about the kind of current state of technology in this realm, there's a number of different ways you can do this. And I think you'll see several of them today. You know, there's a computer vision approach like you saw on the previous slide, and that's a similar approach to what we have here. There's also a full 3D scanning approach using lasers or light scan or LiDAR. And I think you'll probably see some of that later in the additional presentations as well. And there's pros and cons to each approach. And, you know, I think as this evolves, it'll really start to shake out which one is the most efficient and which one we can all kind of coalesce on as a more or less industry standard. So as far as our system, like I said, it is a computer vision based system. So we take blade images as well. We process them through a machine learning algorithm to identify what is and what is not a cutter. And then we apply additional algorithms to, you know, classify the wear, if it's a chipped tooth, worn tooth, good, broken tooth, etc., as well as classify the severity of wear on a 0 to 8 scale. So that's a very quick summary of the technology itself. But what I'd like to take the rest of my time to focus on is what we do with the data, because I believe that is going to be a critical question for this entire exercise. You know, the technology exists to gather that. And like I said, you know, we're going to see that today. But what's really going to set this apart is how we take that information and translate it into insights and design changes that can really move the performance needle. So as far as the current state of where we're at today, we currently have this system deployed all around the world. We spent a good amount of work in 2020 deploying the system, and we have an extremely large database already gathered as far as cutters analyzed, excuse me. We have well over 300,000 cutters currently processed through our system. And the only reason I mention that is that having that volume of data as a baseline, again, is going to be critical to, you know, making improvements. We need to be able to statistically look at the historical wear characteristics in all applications and compare that to new designs and new cutters, and really be able to drive those increases in performance from a statistical perspective. So that kind of brings me to what I want to focus the bulk of my time on. And really, it's just a discussion about some different ways we can utilize this data. And in fact, some systems we're working on developing to give a better visualization of the data and a better automated process for how we can interpret it and drive solutions. So the way that we really look at this is there's kind of 3 levels of analysis you can perform with this dull information that we're gathering that is now on a cutter by cutter basis. At the highest level, you have the kind of application overview. And what I mean by that is at this level of analysis, you're looking at an entire application. You know, it can be Permian intermediate, it can be, you know, lateral section in some area of the world, or it can be narrowed down farther than that. The key kind of criteria for this level of analysis is that you have a fairly wide spectrum of bits of different designs. You have a fairly high number of designs, and you can now aggregate all of that dull information into kind of a single visualization in order to draw insights. And in the coming slides, I'll talk a little bit more about the specific pieces of information we think we can get out at each level of analysis. So the next step down is one we're probably all a little more familiar with. It's more of a design to design type of evaluation. And what I'd say here is what we're going to be really empowered with going forward is that now, instead of comparing one run from design 1 to one run of design 2 to one run of design 3, we can now aggregate all of that information together and organize it in a way so that the performance representation of design 1 is now based on all 10 runs that we have. And the performance evaluation for design 2 is now based on all 6 runs, et cetera. So, I mean, it's really unlimited as far as how many, you know, runs you can include in that analysis. And it gives you a more accurate representation of the performance of that drill bit in that application.
Just 1 minute to go, Chris.
Okay, so I'm gonna speed up real quick. I do wanna highlight this. You know, what I see is really valuable from the aggregate level, and Paul mentioned this, it's really about cutter development at this level. You know, you now have a statistical baseline for how cutters are running in a certain application, and you have a much more accurate view of the dull condition with that mass of data that you have. And that does a couple of things. It helps us develop new technology better that is targeted for those applications. It also helps us select the right cutters for that application, whether it's on the drill bit as a whole or whether it's specific locations on the drill bit. Say we're going to run a more impact resistant cutter in the cone versus a more abrasion resistant cutter on the shoulder. And additionally, it lets us start really taking looks at cross application learnings, and the systems are set up to enable that. And then I kind of already touched on this, but really this is going to supercharge how we can compare designs. It's not a one-off basis anymore. It is a true aggregate view, and we'll get a more consistent evaluation of how our designs are performing across the board. And the key piece, and maybe I'll just kind of wrap up on this before we get to the next section, is you can also start incorporating additional data streams here. You know, dull condition is extremely important because we all kind of believe the fundamental assumption, if you can improve dull condition, you can make a drill bit stay sharper longer, you will improve performance. That bit's going to drill faster. It's going to drill longer footage. However, dull condition is not the only parameter that is important. We need to manage dysfunction. We need to make sure we're achieving our ROP and footage targets. And so at this level of analysis, you can really start bringing in all of those other data streams. And in my opinion, that is the critical piece of this whole thing. That is how we get better by kind of cross-correlating all of those different data streams into insights that will allow us to drive solutions.
I think, Chris, we all agree. Sorry, I'm going to have to invite the next speaker. I just want to make sure that we get everybody the chance within the hour to tell us what they want to tell us. Hopefully, Chris, when the Q&A start, if there are points that you feel that you haven't made that you'd like to, when we start our general discussion at the end of all the presentations, perhaps then you'll get the chance to add some more information.
Yeah, absolutely, no problem.
Okay, but thank you for that. Mm-hmm. So as you can see, the bit manufacturers have been busy. Some of them have partnered with data and technology companies, and we have an example of that next. Our next speaker is Nathan Zanero of Teradata. So you're there, Nathan. We'll hand over to you, and thank you. Okay, we can see your slides, Nathan. We're not hearing anything.
Nathan, you're on mute. You have to unmute yourself.
Can you hear me now? I apologize for that. All right. And
Yeah,
can you see my
now.
screen okay? All right.
Yeah.
Once you share full screen, the controls for your mute go away. So I apologize for that.
They go to another place, Nathan. They're
there you go. So some of you may know me, some of you don't. You know, the last few years of my career have really been focused on helping solve problems that I experienced as a drilling engineer, wanting to use my data in better ways. You know, we founded the OGDQ a few years ago. We spent a lot of time helping the IADC on sensor data stewardship guidelines and things like that. So that's just a bit about me, because Teradata might not be familiar to you. But what Teradata is, and why we're doing this, is because we want to enable people to use data in a different way, and in particular, in this case, bit data. And this is part of a larger a solution for us that we call industrial forensics. So we're working with folks like Boeing on inspecting airplane parts. We're working with utility companies on vegetation management using computer vision, and with you know, transportation companies and things like that. And so we started from the bottom up in our approach to building this, which was to make sure that the data could be connected at its core with other things, with ERP data, with sensor data systems, with manufacturing data systems, and that's where we began. And now we partner with others to acquire image data, to acquire sensor data, and to bring those things together into a larger whole. What we're trying to do with the particular solution around drill bits is really three things. One is to help our customers have a way to inspect bits before they're used. Bit grading is important. It's important for redesign. It's important to understand the damage and the wear and the characteristics of atomic level components, cutters, blades, nozzles, non-cutting elements, everything that is a piece and component. But it's also really important that they have an opportunity to inspect and evaluate things before they're used, because a bit that is damaged or defective should not be run. So we want to provide that as well. And then of course, to combine that with sensor data, with BHA data, with product data, and to feed that back into redesign, and to not just redesign, but perhaps even modifying how things are used. To do that, we had to build quite a few components. So we tried to standardize as much as possible. Standard work, so image acquisition, standard process, making sure that we can easily acquire data for joining it to other systems of record. So a mobile app will show. Standard analysis, we are going to contribute all of our work in grading and how we approach that back to IADC. Standard access, so all of our things are going to be API based, and we'll show that so that you can use the data how you want. A standard data model, so kind of third normal form integration. If you're an IT professional or you understand what that is, you can understand that that's really important when you're trying to join things, and a standard business model. So starting with standard work, we view our solution for acquiring images as a means to an end. And I want to be very clear about that, because Teradata is not a hardware company. We don't want to make things that go out to drilling rigs. And in fact, we have partners that do this for us. So this was for us a way to acquire this data, but the way we've built our system can accept X-ray data, could accept laser data, could accept image data, anything that creates image sets or point clouds or vector-based data sets fit into our workflow. And so this is just one example of the workflow that we've built. So in this case, we acquire a bunch of images. It's a single button, takes a few minutes. We get about 4.8 gigapixels worth of data. Each bit has 8 to 10 million individual points in a point cloud, and each cutter generally has around 8 to 10,000 points in a point cloud. And so we can use those point clouds to create vectors, and we can project images on them and do all the things that you would expect from computer vision. Then we built a workflow so that the people on the rig can interact with this device very easily, so that they can acquire data, tell us, what is the bit, what is the rig, what is the bit run, so that we can join it to a WellView system or an OpenWell system, whatever that may be. We offer a lot of quality control around it. So we want the people on the rig to be able to make sure that the pictures they took were of sufficient quality, so that they don't have to do rework. And then a lot of ability to review the results on a mobile device. This is all mobile first and mobile friendly. So our AI solution is really focused right now around images, but again, we take the images and we turn them into 3D models that are point cloud based and vector based. We do semantic segmentation, so we break the bit into its atomic components. So we identify cutters, primary and backup cutters. We identify non-cutting elements, junk slots, blades, nozzles, and shank. We then can take each one of those atomic components and assign it its own set of meshes and its own set of point clouds and its own set of descriptions, so that you could ask to view each item atomically. You could do full cutter by cutter, non-cutting element by non-cutting element, blade by blade, each one of these things independently. And that way we're also not having to always recall all of the images or all of the data. So it makes it much more performant. We do follow the conventional ordinals. So each blade is numbered correctly as you would currently number it according to IDC guidelines. Each cutter gets 2 sets of ordinals. One is a radial ordinal, which is often used by the drilling bit manufacturers, but it also gets a per blade ordinal. So if you wanted to ask for cutter 1 on blade 1, you could do that. We do segment the blades into their distinctive zones, and so that you could ask for just the blades or just the cutters on the cone section or the nose section or the shoulder section. And we've been very effective at classifying cutters. Most of our work thus far has been done in the laboratory setting, and we've scanned a lot of 4D cutters, ion cutters, things that are non-planar, things that are non-circular. And we're extremely good at being able to differentiate between those things, and also to be able to identify types of damage, which are in some cases similar. Right, and part of the benefit of the approach that we've taken here is because we are designed to do both inbound and outbound scanning. We can identify shaped cutters before they go into the well, and we can identify changes to shaped cutters after they come out. So that removes some of the confounding elements we see when dealing with shaped cutters or things that may have been damaged before they were used. And then we put all that into a relational database, and that's really important because now as an organization, you can use all of the talent that you have in SQL query writers to join data, to query data, to do the things that you want with it without having to learn new skills. We've been very accurate in our ability to detect things. Our F1 scores and our precision of recall are within the acceptable and very good ranges that are generally prescribed by data scientists. So we feel confident that as we see more types of damage and as we want to describe more types of damage and as the IIDC conventions mature, that we'll be able to mature along with that. And we really think that to get the value out of this, that you have to join it with other data, right? And that has been our mission from the beginning, is that we do want to join it with other things. So our data model is something that is really interesting in the way that we've developed it. We do provide security on a bit run level. So we're not a bit manufacturer. And so we will be taking images of many different types of bits from many different manufacturers. Security and the ability to share that in ways that honor existing contracts is really important. And so we manage that on a bit run level. So if there are tight wells, if there are secrecy requirements, that can be managed by the customer without Teradata having to be involved. We do have explicit joins for time series data, for like WITSML sensor data, explicitly joinable with PPDM and OSDU compliant semantics and views, so that you can easily join it with Wellmaster, with BHA data, with sensor data, ERP data. All of those things are built in. And like we said, because we have built our workflows so that they work on point clouds and vector volumes, we can accept things like X-rays or MRIs or any kind of data set that you could create to image these bits, we could consume as part of our workflow. And then we do have every primary atomic component, again, has its own mesh. So as we go through this, we can view these things independently. We can run analytics on them independently. We could design different classes of image analytics for different types of meshes and different types of volumes. And most importantly, for the wear and damage, we do support multiple different types of damage and wear on every atomic component. So you could describe a cutter as having both chipping damage and thermal bond damage. And each of those damage classes can have an ordinality. So you could describe which one is most present or which one is most important for analysis. They could also have a severity level for each damage type and an extent. So there are multiple dimensions to every type of damage, and really any number of them could be present at the same time. So where we're at with this is we have had a unit, an imaging unit deployed in a bit repair facility for several months. We've been doing alpha testing. We've imaged quite a number of bits already, and we've been developing against that. We're ready to start deploying some larger scale laboratory testing in the US and in other places. We have a partner that's going to be working with us on that as early as next week. And then we're looking for rig site beta testers to, at the operator level to do some testing in the field so that we can do both inbound and outbound testing. And we'll be ready to do that in Q1 of this year. And that's all I've got.
Perfect. Thank you, Nathan. I think we're picking up a theme here, aren't we? That the bit data is is not isolated. It's a lot more valuable when it's with the rest of the data that we're getting out of the drilling process. Great to see application of such advanced technology, and we're about to see some more of that. For our next speaker, many of you on the call will be familiar with the RAPID consortium of companies that make up a group that's run out of UT in Austin, and one of the driving professors of that group is Pradeep Ashok. One of their many projects is dual bit imaging, and so over to you, Pradeep.
Thanks, Robin. Of course, Eric and Isabel, two of my other colleagues on this project, are on the call as well, so they can answer some of the questions as well. So I'm going to talk about the bit image processing research that's currently ongoing at UT Austin. And of course, we have heard today already that the problem with the IADC dull grading system is twofold. One, it's subjective. And second, it does not really capture all the information about the bit. And so for the most part, these are the two things that everybody in this call is trying to address. So our research objective was to automate the capturing of the images of the bit, and then to use machine learning and image processing to classify the damage in a standardized way. That was one. And second was, like Robin said, couple this information with other drilling data to actually figure out what caused damage to the bit. So towards that end, we decided to primarily go with 2D images that are basically captured generally with mobile phones. And so it really consists of 2 steps or 3 steps. Capture the image, right? And then identify all the cutters in the image you can see over here, and then grade each of those cutters. And when we started off this project, our goal was to use these images to see if these 8 categories can be filled out, because we're trying to, of course, remove subjectivity. Towards that end, we used YOLO V3, which is a convolutional neural network, to actually identify the cutters and the places where the cutters were completely removed in these images. And we found that we were able to get really, really good accuracy, greater than 97%. And when we combine that with some heuristics, such as you identify the blade and you see that there is some empty space in between, so there's a cutter there, we were really able to get pretty much all the cutters identified. We also kind of went one step further and identified the location of the cutters on the blade, because that's also kind of critical, as you'll see later. And a lot of this work is already published and is going to be also presented at the IADC drilling conference that's coming up in March. So all of this is published. So once we identify the cutters on these images, the next thing we do is basically cutter damage quantification. And for that, we used image processing. We primarily did some pre-processing and some binarization. And then we used OpenCV, some functions such as get contour, fit ellipse, to get the contour of the damaged bit. And then we compared it with the original shape and get a good cutter area percentage. And that kind of helps us grade the cutters. So in general, if we have a set of cutters, we are able to detect all the cutters and then grade them appropriately. So essentially, for almost every cutter, the grade that we kind of gave more or less kind of matched basically a human expert's grading. And of course, going back to the fact that the whole purpose of this exercise was to remove subjectivity and have the algorithm kind of grade every bit similarly. So just to step back, we're trying to see, so can we actually automate this IADC dull grading process using image processing? And what we saw was that basically the first 2 is possible, and we have shown that and it's published. The next one is also possible. So basically the location of the primary cutter, that's quite straightforward. And these are basically from 2D images taken with mobile phones. This one is basically the dial characteristics. We have to do more work on this, and we haven't actually gotten to that stage because our set of images that we can work with is quite limited, unlike a lot of the service companies who have access to the bits. But that's something we're actually going to be working on this year. One thing that we cannot really do really good with 2D images is to get the gauge. But there are some ways we can get around it. You could put scale markers like these on each of the blades. And if you were to take the photos then you can actually kind of, get an idea as to the volume. And we did not concern ourselves too much with bearings and seals because we're primarily focused on PDC. The recent pull really requires other contextual data. So really, if need be, we can actually get quite a lot of these 8 categories kind of, identified. So of course, the next step is basically, let's say, you identify the cutters, you identify what kind of damage occurred to each of those cutters. We can actually quantify those damages to actually arrive at root causes. And so we've been, again, the data set that we have worked with is kind of limited, but with the data set that we have worked with, we have come up with some preliminary algorithms to actually, whereby you take, the 6 blade images and basically it instantaneously tells you, hey, highly likely that, this bit went through whirl. And of course, at this stage, we have not combined it with, the real-time drilling data yet, but that's something, that we'll be adding in the near future. And then, of course, you can see a decision tree here, and decision trees are kind of, really transparent. So, also helps you kind of understand why the software said what it said. So again, I know some of you had questions about cell phone images, right? Yes, when you take images of the various blades, you do need to do quality control. And people have already figured it out for things like checks, right? Basically, if you take the image of a check that you want to deposit, and it's not good enough quality, it gives you pointers like, go to a place where there's light or use a different background, etc., etc. We can do the same thing now for blades. Really, YOLO V3, the neural net model can be run on Android phones and iPhones. So as you take the picture, we can identify the cutters. And so basically, we can have the software ask the user to kind of make sure that the images taken are appropriate. So it kind of makes it a lot more intelligent. So I know a lot of everybody here is kind of working towards upgrading the grading. And so just kind of as a throwback, and if you go back to 1987, the original work group, what they said was basically the objective was to facilitate the creation of a mental picture of a worn bit's physical condition. So back in 1987, there were no mobile phones, right? And digital images was basically not commonplace yet. So, and that's why they had to kind of have a system like this to basically communicate what happened. So, of course, given it's 2020 and in 2030, I doubt that we would even need something like that. But would it be possible that we just have images that are taken and stored in your data store? And I kind of again, we can of course definitely have both, but the real question is, in 2030, do you still imagine seeing something like this, or would you just have a set of nicely curated bit images in your data store that you can kind of go and see and figure out what exactly happened? So that's my quick brief introduction to the research that we are doing at UT. And a lot of the software that we have there is acceptable. The Rapid members can actually log on to and kind of upload their bit images to kind of get a feel for how it detects the cutters and the grading and such. So That's all I had, Robin.
Right, thank you. And thank you to Isabel, who I know has done a lot of work on this. And if she's in Australia, it means it's the middle of the night. So sorry to keep you up. So thanks, Pradeep. So we've heard a lot about the analysis of cutters. So what about the guys that are making those things? So our next and our final technical presentation is Brandon Linford, who is from US Synthetic. So I'd like to hand over to you, Brandon.
Hello, everyone. Thanks for having us talk. We want to thank the IADC and the IADD for inviting us to share. This is a very important topic for us. I assume you guys can see my screen.
Yep.
The question of the day.
Oh, there you go. That's it.
So I'm the Director of New Product Development at US Synthetic. This is a topic that we're very excited about. We're excited that there's a lot of momentum going forward for updating the IADC standard. We rely on this data to make a lot of decisions around how we continue to improve our products that ultimately improve how well we can drill. And so I want to walk a little bit through kind of our vision for how we see this being beneficial to the industry and a product we're developing to try and help the industry improve. So as many have talked about, the need for better data, it's really a moving target to understand what is best. Operators are continually changing the parameters and areas they're drilling in. Bit designers are continually improving their bit designs, and we're continually improving our cutter design. And so as those things change, what's optimal often changes as well. So at US Synthetic, we have a manual process we follow called application-specific design, where we try and be scientists in how we follow, how we improve products. And it starts with listening to the bit. So I love what Paul said about the bit. There really is. There's so much data locked into that dole. It is the most important thing for us to look at for determining what went wrong and how can we make it better. And so in our process, we spent a lot of time looking at the dole of the bit, and individual failures modes are on that. And we do this typically in a manual process. It takes about a half hour per bit to analyze, put the report together, look at the data. But we do that over and over again, and we can get a pretty good picture of what's going wrong and what we can do better. We then take that back to our lab and with forensic analysis, understand the root cause of what's happening, replicate the failure with lab tests, then analysis with hypothesis testing to build trade-off curves that then our customer engineers can then design new products that ultimately improve the drilling performance of the bit. And we've demonstrated that we can do this over and over again, and we've developed sets of solutions. And I like to use the golf club approach where our customer engineers working with our drill bit customers can make recommendations of, do they need a driver or a putter for this application? And they're always working on updating those set of clubs as well. This has all been good, but it's slow. And honestly, it's slower than what the change at the rig site is like. And so when we look at how can we be better contributors and improve value for the industry, to us, it starts with the bit and understanding how we analyze the bit. And we can only deeply analyze a few bits doing this manual process. So we wanted to develop a tool that allows every single bit to be analyzed deeply. And so we can do data analytics and engineering analytics on that data to help us drive and improve, as well as help drilling engineers improve and drill bit designers improve. And so our vision for how this goes forward is we want to build a system that allows every bit to be analyzed. When we start thinking about what it takes to analyze every bit, there's a lot of logistics problems that come into play. And so we worked on a solution that helps us get to a point where we could produce a report like you see on the right on every single bit, and ultimately enable drilling bit and PDC engineers to solve problems faster, and even more importantly, once we make a change, to actually see that change mattered. So I'm going to walk the group through our latest demo. We've been working with a partner called Exofield. They're an oil field software service provider. And over the last few years to develop a solution. We're still kind of working towards a beta phase, so it's still in development. There's still places to go, but we're going to show you where we're at today, and as well as talk about where we want to go in the future. So hopefully this plays. So again, our solution is a mobile phone, and we chose that because it can be done on any site. It can be done in a shop. It can be done on a rig site. It's relatively inexpensive. It's the cost of a phone to put it in your pocket. So you literally can have hundreds of people around the world that have access to this technology. And on the phone, we're using AI to look at, measure the diameter of the bit, measure the blades, take a picture of each blade and identify the cutters. I think that's been covered multiple times today, how that technology is ready to go. And all this is happening on the phone without cellular connection. So you can see here that we've identified the cutters. There's still a lot of user ability to edit because as most people have said, we need lots and lots of images to refine the AI. And so we're going through that process. But from the picture on this blade, then the AI will be able to recognize what's the good portion of that diamond and then measure the wear, as well as to start looking for what faults. Is it chipped, broken, spalled? Right now we're measuring percent worn. We think that's a better way than the current IEDC standard, but we're building that IEDC standard into it. But that's one area we'd like to look at standardization, or how do we get a better quantifiable way of measuring wear of a bit, cutter by cutter. And so you can see here, it's identifying what's the good portion, what was the original radius of that cutter, and then we're able to see what's missing and give an estimate of what percent worn that cutter is. So there's a lot of work going on here. It takes a lot of effort to try and get this to be accurate. You can see here, we missed the up drill cutter, so the user's adding an up drill cutter. And so we're going through this process over and over again, and every time we go through it, it gets more accurate and more reliable. That's kind of what we're in, the phase we're in. To kind of demonstrate the usability and versatility of this is we can scan a bit in pitch black. This could be on the rig site. We're using all the sensors on the phone, not just the camera itself, so we can see the bit in the dark. We can use the flash on the phone to illuminate the bit and take decent pictures. And so this can be done in a dimly lit warehouse or on the rig site, as well as in a well-lit shop. So again, to our vision of every bit being scanned, we feel like we have to have a tool that can be put in lots of people's hands and be versatile enough to be used in many different conditions. And so we're trying to demonstrate that here. One of the next challenges is recognizing faults. And so we're training the AI to recognize the different IEDC faults, as well as the ones that we're looking at Geosynthetic. So that's an area we'd like to get some standardization around. We also think it's good that if we're using AI to identify faults, that we publish the probability of that fault. So not every time the AI says, hey, this is a spalled cutter, is it 100% spalled or 100% chance it's spalled. And so you'll see here on ours, we're going to show the bounding boxes in a second. And we're going to show what the probability of that failure actually being what we're saying it is there. We think there should probably be some standards around thresholds for how sure are we that that failure is accurate as we declare that in the standard, in an impartial standard. That'll show up in just a second here on this video as we're walking through it. So right here, you're seeing that we're showing that this cutter is worn and delaminated. It's clearly not delaminated, so the user is going to come in and delete that, but it's showing there's a 7.5% it's delaminated. It's really low probability. And so as we go through this training, we expect this to get more accurate, but at the same time, there probably should be agreed upon thresholds for, as you see, there's multiple developing AI solutions, probably some level of standardization around how do we declare what is what, if it's going to become an industry standard for digital analysis. The first phase of this project is really to scan a bit and produce a report. So this report can be sent out in a PDF, emailed, text out, really easy, can be done less than 10 minutes. This would be the work that a typical application engineer would do. It might take them 40 minutes to an hour to put together. The next phase we'd like to get into, which many people hit on today, is how we actually use this data, which is the data analytics piece. And that's what we're working on now as we finish up this first phase. So that's kind of our demo. The next, we have some outline of what phases we're in. We're expecting to do a beta release this quarter, or we have a few bit companies and operators who express interest. We expect to put some phones in their hands. They can use it, give us feedback. We'll refine and improve that model, and then have a commercial release hopefully near the beginning of Q3 on that first phase, which is scan and report. The second phase that we're starting to work on now is how do we use that data, which is the data analytics. and engineering analytics. How does a drill bit designer use the data? How does a cutter designer use the data? How does a drilling engineer use the data? Those are all areas we are really excited about and think there's a lot of potential for. We also listed a lot of different areas where we think, hey, there would be some value with all these people developing technologies to agree on some standardization. And we won't have time today to go through all of them, but we listed them here. So when this is published, we can look back at it and kind of see the things that we're advocating for some standards on that we'd love to see in the IDC standard. So that's our presentation. We sure appreciate the opportunity and time to present to everyone. If anyone is interested in what we're doing, please reach out to me. We'd love to spend more time with you. Thank you.
Thank you, Brandon. And thank you to all the presenters. I know it's been tough. Some of these are very technical, and squeezing all that into 10 minutes has been a bit of a challenge. And so I appreciate you all doing that for us. Thank you. We've now got about 15 minutes of open discussion. Thanks to all those who've been putting the questions in the boxes there. I'm going to recruit some of my colleagues now to pick out some of those questions for us. So first of all, to Robert, have you found anything interesting there you'd like to raise, Robert?
Yes, I did, and I think based on the subcommittee that I'm pushing for is it was a question by Maxime. Well, the last name is Selenchika. Sorry if I pronounce it not right. Any proprietary issues with 3D scanning of drill bits of different providers? And there's two answers provided already, which I read quickly, and maybe somebody can add to that. Is from Paul. Is there concerns from some bit vendors for 3D models, but it's not done by all scanners, and the model can be held private? And Sean Emery answered, in the track system, we do not provide a 3D model. It is stored securely in the cloud. All that's presented is the difference between sharp and dull as a percentage, as well as all the IDC grade characteristics and advanced graded enhanced solutions. So any more remarks from the audience or the presenters about proprietary issues with 3D scanning and in general proprietary issues with doing this? Because the more we measure, the more gets out in the open, and it's something that is proven to be sometimes an interesting discussion point, to put it mildly, between partners.
Yeah, further to kind of what I said there, essentially in our system, we segregate it on purpose, and we did that from the outset because of those issues with proprietary concerns from bit vendors specifically. I think it gives us a bit of a unique position in that regard because we are separate and agnostic in that sense. So from that perspective, we were able to segregate that, and all that the output is a difference between sharp and dull, and it's just a percentage as well as all of the characteristics. So I think that meets that need of proprietary protection of IP.
Yeah, and Robin, I think it's a great point to bring up, and we take a slightly different approach on that at Teradata. I think that you know, the operator is aware of their relationship with their vendors, and if an operator acquires these images and has contractual permission to share back to the bit vendor, or with whomever, we won't get in the way of that. We won't directly facilitate. We're not going to expose anyone's intellectual property in any way, but we do think that, and I think Paul Pastusik says it quite a bit. The more that this information is shared, the more that rising tide lifts all boats. And so we do want to find ways to make information as widely available while still protecting IP.
Yeah, I think it's interesting. I often use selling a drill bit as an example of where you draw the line between shared data that is beneficial to all and proprietary data. I think that anybody who's sold a drill bit will know that when you walk into an operator to see a drilling engineer, you'll quite often see bit records that have other bits on there. your competitors' bits on there with their performance. So that's how far it drilled and that's how fast it went. What you don't see on any of those is how that was achieved. What were the intricacies of the design of that bit? So the performance data being shared clearly was benefit to all, and it was clearly benefit to the operators because it let's face it, it made the drill bit manufacturers extremely competitive. They're always clambering over each other to improve on the next run. So that's, we've seen the benefit of the sharing of the data. But from a drill bit manufacturer's point of view, you also see the benefit of being able to hang on to your proprietary data with regard to the exact design features, the chemistry of the matrix, etc. So I think we're at a similar position here, whereby we'll see lots of, with these data measuring methods, we'll see lots of proprietary methods of, and we've seen some already today, of measuring the data. What the IDC here is trying to achieve is how do we come up with a method of describing that data that we can all universally agree upon. So thanks for that, Robert.
Yeah, can I just want to add something too that I think is kind of related. If you notice who's on this this session, we've got cutter vendors, bit vendors, academic institutions, UT, thank you. But we've got a broad spectrum intentionally involved in this effort because we recognize, let's say, and I'm gonna pick on the U.S. synthetic guys because we've had a number of discussions with them on this. They may only get their feedback from the bit vendors. They don't necessarily get the data from us operators. And yeah, okay, Exxon's been as maybe the worst in the business about not sharing things in the past. And I'm pushing very hard within our company as we have some very good high-level managers that are doing the same thing to start sharing a bit more openly, because we do recognize that if we share with you, you know, the application, the details of you know, how we ran the bit, whatever else, that, and if it goes not just to the bit vendor, but to the cutter vendors can improve as well. And we don't, I don't have to know which cutter vendor you use if you're a bit vendor. Most of the time I do anyway, by the way, you know that. But the idea is if I can go up and down the entire chain directly without isolating this data, I think we're gonna continuously improve faster and faster. And I think that's that's our goal. So, and by the way, that's true. I've had this exact same discussion with motor vendors. Most of the time, they don't know what the mud is. They don't know what the, you know, whether we were running stalling all the time. They just see the dull and don't know what happened to it. And so I'm intent that we try to open that up as much as possible. And yes, we do have to respect people's IP. I think that's a given.
Great. Thanks, Paul. You got any more questions for us, Robert?
Let me see. I think one of the more technical ones is the use of cell phones to do the scanning. We had two competing statements, and maybe both gentlemen can shed some light on why it's working and why it's not, and why somebody says I need to have a very precise scanner on site, and why the others say, okay, we can use a cell phone. Because to me, it looked like the results are more or less the same if you look at the colorful graphs.
Yeah, thanks. Any comments on that?
Yeah, I can provide some initial comments on those. Of course, I know Brandon can also kind of give some real good insights. Most of the photos that we have analyzed at UT are basically photos that have been picked up from cell phones, and for the most part, we have been able to kind of identify the cutters and also the damage on them. There are times when the lighting is bad, and there are times when the blades are kind of photographed from strange angles that cause issues. But if you can control those, it looks like we can actually get 90 to 95% of our goals, which is basically to figure out what happened to the bit and what improvements we can make from it. Of course, there's always going to be with 3D scanning more sophisticated information, but we expect technology, especially on the software side, algorithm side, to continue to improve. So we'll just keep pursuing that from UT side.
I'll jump in a bit too, because at Teradata we've tried 3 different approaches so far. So we've done very high-end industrial cameras. We've done cell phone cameras, and we've used GoPros, both still and in motion. And all 3 have different things about them, right? They have very different signal to noise ratios. They have very different software interpolations and interpretations that affect images, and different ability to process different levels of light. And so where we stand now is that to get the level of measurement accuracy and confidence in analytics that we think the industry requires, we've kind of settled in, for the time being on kind of a mid-grade industrial camera, really low-cost application. But we fully intend that in the future, cell phones will probably become, the cameras will get better. They'll include LiDAR. There'll be other things to correct them and increase the signal to noise ratio so that we have a cleaner image from them. And I think any application that comes to do this work should be able to accept that inevitability, right? It should not be built solely on a single type of image acquisition or photogrammetry. But also, I think what the US synthetic team knows too is that there are other forms of EM imaging and other forms of perhaps non-EM data acquisition that could be used to gather information about the bits, and that needs to be able to be incorporated as well. So yeah, for now, that's kind of where we stand, is that high quality structured image acquisition is most likely to yield quality results, but in the future that may not always be the case.
Thanks, Nathan. I wonder if some of this is going to be driven by the speed with which we need some analysis. I mean, maybe this might be for Paul and Dustin, or even for Chris and Will from the bit manufacturers, because there are times when you pull a bit and you need to make a decision pretty quickly as to what you're going to run next. And so sometimes you don't have the time to do something. Maybe pull out your special camera if it's not on location, etc. So I wonder if there's some comments on how urgent it is that we have analysis in some cases that we can do, within maybe 20, 30 minutes.
Yeah, so, go ahead, Chris.
I was just gonna, I'll comment on that. I mean, I see Paul responded to one of the questions in the comments, and I just kind of want to echo his statements, but I really see there being 2 kind of unique uses for this. One is that quick turnaround rig side report where you need to get your phone out, you need to be able to take some pictures, and you need to be able to have that report in your hand immediately, basically, to make a real-time decision. And so I think many of the systems presented today are capable of that. That is, we've seen that the technology exists from photos, whether it's a phone photo or a standalone camera or some kind of fixed setup. Technology is available to assess PDC cutters and classify them. And so that is very much possible on phones for that kind of quick turnaround report. And I think that's where we're all headed in some ways for that kind of initial use case. The other piece of it, though, is this kind of more in-depth, larger scale root cause analysis. And you can still use that rig side information to feed that, but ultimately that's going to have to be data-based. That's going to have to be correlated to other parameters like dysfunction, drilling parameters, weight on bit, lithology, back rake of certain cutters, cutter spacing. All of those things are going to have to be cross-correlated to this dull information library that we're gathering in order to really make changes on a kind of massive scale. You know, the initial use case allows you to make a better decision for bit A versus bit B, what you have sitting on the rig. But ultimately, where we want to get to is, you know, we are consistently moving the needle up in performance. And I think, like I said, that's where this kind of larger approach of being able to correlate to all these different variables is really going to come into play. And some of the more advanced systems, you know, with the point clouds and everything else, give you more information to do that type of analysis. So, you know, I think there's a use case for both, I guess, is just what I would summarize as saying.
I think I would echo Chris's comments there as well. This is Sean Emery from Trax. So it's the classic example of, you know, the better the sensor, the less the AI has to do, right? So at the end of the day, you want to have the best sensor possible if you're trying to do a true forensic analysis. If you're doing a spot check, well, the phone is definitely going to be good, and it's nice to be able to do that. And I think that's something that all of us have gone down the road of, right? It's just the question of whether or not we're trying to advance the IDC protocol to a point where we are going beyond, and like Chris says, you know, moving that needle those next couple of steps. So I think I would echo kind of some of the things that Chris was saying there as well, as far as the sensor is concerned, yeah, as well as echo some of the things that Nathan was saying.
Great, thanks, guys. So in the limited time left, we're going to consider how we do this. Obviously, this requires work. It's going to require subcommittees for the IADC committee. There's some thought gone into that already. So I'd like to hand over to Paul, and you can tell us what you think about the subcommittees and work groups that you've been considering, Paul.
You bet. Okay, so, you know, again, I think the key thing here is to get to a forensics kind of workflow. I'm going to credit Dustin and Mark Dykstra, by the way, for, you know, let's start with the end in mind. What do we really want here? What we really want is to be able to, you know, make this continuous improvement process, both, again, you just said it, Robin, instantly or near instantly while I'm on the rig, and then the longer term one as well. So we need to support both of those. I think that one thing that's important, we need to focus in this IADC effort on classification and characterization, not hardware. You can see how many people are working down the hardware issues and hardware says software. I think what we want in terms of the output for this project is we want agreed upon classifications, we want agreed upon ways to store the data, and agreed upon case studies that we can use and examples for training and learning. Now, the training examples, if we have training examples, they can train machine learning systems or they can train humans. It doesn't matter to us, I think we'll have humans in the loop for quite some time, but certainly I would imagine over the next decade, and maybe that's shortened a lot less than a decade, but I certainly can see the way forward to having, you know, automatic detection on cameras and scanners and such, and probably in your hand. I don't think it has to all be a scanner-based system, but hey, we're not there today yet. So that said, there were a couple of things that we really wanted to talk about in terms of kind of the key task. One is to create a set of case studies, and this would be we need volunteers. Basically, the deal today is to get volunteers to work on these different subjects. And if you think about the case studies, what we're talking about is not just the data, not just photographs, but the digital data that goes into that, the well path. In fact, in many cases, Isabel Whitdoring's on the line here as well. Isabel was a summer student for us, an intern, and she's on the rapid team at UT as a master's. She did a lot of work correlating cutter damage to digital signals, and of course to rock strength. And one of the questions that came up was, you know, how much does the rock property affect the dull? Well, it's kind of everything. You know, I'll give you a good example. I can whirl like crazy in 5,000 PSI rock and never see cutter damage. But if I whirl in 40,000 PSI rock, I got about 20 seconds. So I think the recognition is that we need to create some case studies. That's kind of one thing to do, and that needs to be created, shared, curated, and use that for training, both internal and then external, to both to you know, other groups within the industry. So consider volunteering for to support case studies and that committee, if you will, and that's to volunteer some of your data. But it would be you know, take a folder. Just think about taking a folder of data, put everything in there that's needed: the bit, the BHA, the formations, the drill pipe size, you know, what motor it is, everything that adds to that, not just photos. Okay. And then creating a workflow, a forensics workflow from that. I have been given the authorization. ExxonMobil, we have a forensics workflow, and I teach that internally. I've been given the okay to use that as a starting point. If this team so desires, we can share it and then expand it. It's certainly not complete by everybody else's standards, but it meets what we needed. But anyway, that's open to us as well as an option. So that's one. We need that case study subcommittee. The PDC codes. I need to expand a little bit on what Isabel did for us for the summer as part of her internship. She met with all of the major and most of the minor cutter vendors, all of the major and most of the minor drill bit vendors as well, and sat down and said, all right, can we agree upon, if we take a picture that looks like this cutter, can we call this, can we say, agree upon the name, agree upon the root cause? Is it thermal damage? Is it mechanical damage? Is it thermomechanical? Is it spalling? Is it loaded tangentially back through the carbide? You know, what's the direction, so that we can do that. She has a draft of that and has had it actually ready to go since before Christmas, and I've been off and haven't finished editing it for her. But that is to be shared with everyone as a starting point on this codes, to be able to look at, and that's just for the cutters, but you can imagine we need to do the same thing for the gauge pads and other elements as well. But cutters tend to be where we focus a lot of effort, because you know, we can see, we almost always see cutter damage, even if nothing else is damaged. We got to deal with that. So we need a subcommittee around working that issue on those codes and subcodes, and again, creating a training data set and a user set, and then ultimately sending it out for comments. Like I said, we have a very first draft just sitting almost ready to go out here back to the original contributors. So anyway, those are the first two subcommittees I need to talk about.
Thanks, Paul. And Robert, I think you got some thoughts on another work group we need. Hi, Robert. Don't know if you're on mute, but I'm not hearing you.
So could we share that table we created for all the subcommittees?
Yeah, sorry, I don't have a table. Have you got it there? There you go.
Opportunities. Here we are. So that's the storage committee, and basically that revolves around we're creating massive amounts of data, and we need to be able to find a way to store it so it's accessible from a variety of different basically contributors and also basically users. It's diametral to our efforts here, basically working together, and then every vendor has its own proprietary standard to access the data. So it's not about how to store the data. It's creating like the daily drilling report, the automated one, a form of, okay, if you store a picture, it will be in format XYZ, and these are the fields that we're willing to share with the rest of the world. And if you want to access them, this is the way to do it. It's a big discussion. I think, and it's critically important for the success of this whole effort. Because you can make the best predictions in the world, but if nobody else can see it, then its relative importance is going down. So that's a committee that I would like to push. It has a link with the IADC because we want to do the same as with the daily drilling report, not only a revision of the codes and the structure, but also offering a standardized way of accessing it. And in the daily drilling report, that's an XML schema. But this can be entirely different or the same. It depends on what's the best way forward. So we stay away from the IP. Everybody uses their own IP and then their own property. So you're only sharing what you want to share. But if there's sharing to be done, it would be nice if it can be standardized.
Thanks, Robert. So you'll see the last two bullets on there. A thing called phase 2, which is when we start to look at BHA, where those of you that have seen the slides from Paul in the past will know you can read a lot into what you see on stabilizers, motors, and other downhole components. So how quickly we get to phase 2 will depend on the speed with which we complete phase 1. So the consolidation and finalized proposed codes, which we aim to put into an SPE paper. So the March 2022 date there is the SPE IADC drilling conference, where ideally we'd be like to be in a position to present a paper on all that we will have achieved in the meantime. So you'll see the contact details at the bottom there. Please volunteer for the committees and subcommittees that you've heard about. I'd like to once again thank all our contributors today. Someone put in the chat box about roller cones, which is a good point. So they will also be considered. Please go to the poll if you can, the links in the chat box, the one that Dustin put together. Thank you. And thank you once again to the IDD, and I'll hand you back to Jim.
Hey, great. I want to add my thanks to everybody for helping to put this together. I think it's been very interesting and informative. I've had discussions with the committee that I think we should probably make this a fairly regular event. Obviously we'll change the topics and so forth, but I think it really helps to keep the momentum up on these types of initiatives if we can report back and kind of keep it in front of folks. So with that being said, if there's no further questions, we're going to go ahead and shut it down. We have a fairly aggressive schedule at IDD here through the first quarter. So take a look at the website and you can see and get updated on all the events that are going on with there. So again, thanks to everybody. Everybody have a great day.
Great. Thank you, Jim. Thanks, everyone.
Everybody.
Thank you.
Thanks a bunch.
Thanks, everyone.
Yep. Thank you all.